Okay, so we are starting our class today, and first of all, let me know if the audio quality is fine. If you can hear me properly, please let me know in the live chat. If you can hear me properly, let me know. If there is any issue, please let me know. Okay, so thank you very much for letting me know that the audio is working properly because that's one of the most important things I'm concerned about. Okay, right. So during the class, if you have any question regarding anything, please let me know in the live chat. So there is a slight time delay between when I am recording this video and when this is streamed to you. There is a slight time delay. So I will be answering your question. So don't worry about that. And again, after I ask a certain question, I would wait for a while for all of you to actually sync up to the stream. So and again, this is my very first live stream, so I had to learn a few things before actually going into this. So there might be technical difficulties for me actually. Anyway, in any case, uh, and as it seems this is going to be the new normal for a few more weeks, I think. Also, the stream quality, the video quality is fine, I think, right? Even though I'm streaming at 720p, let me know if you need higher resolution because I can arrange that. Okay, the internet has become pretty spotty after the recent global pandemic. Anyway, so I'm streaming at 720p. I could have the resolution up if you wish, but let me know if the stream quality is fine. Thank you for letting me know about the audio quality once again, and good afternoon to you, all of you. So we shall wait 2 more minutes and then start. And one more important thing, all these videos shall be available to you for watching anytime you want. But if you watch it live, you would be able to ask me questions directly. So that would be one of the advantages. But in any case, if you are unable to join us today, you can watch the video later on. So we shall start shortly. So right now we are starting then. So right. So in today's class we shall be learning about period. So we have already learned quite a few things. So in today's class we shall be learning about periodicity of signals, and we shall talk about energy and power contained in the signals, and we shall talk about even and odd symmetry of signals. So this is going to be a very basic class. We shall not be needing much of any hugely complicated mathematics. So don't worry about those anyway, and it will be a relatively simpler classes anyway. So we are starting. So we have a question first of all. So let's start our discussion with a simple question. Question is, let me know what is the period of this simple thing. Say I have a signal which is xt and this is just sine t. So what is the period of this signal? I believe all of you already know the period of this signal. What is the period of this signal? That's 2 pi, right? 2 pi seconds to be exact. So what does it mean? It simply means that after every 2 pi seconds, the signal repeats itself. So the value of the signal will repeat itself after every 2 pi seconds, right? So with that said, so for this signal, I can very easily say, since xt is equal to sine t, I can very easily say for this signal, I can write xt plus 2 pi is basically equal to xt, because after every 2 pi second interval, the signal will repeat itself. This can also be said like this. So since the signal repeats itself after every 2 pi seconds, the signal will also repeat itself after every 4 pi seconds. So that's 2 into 2 pi seconds. That's also xt here. We are talking about sine t, simple sine t. So understandably, this is also true, right? So we can say something like this very easily. We can continue this way, and we can say that okay, we have this situation: xt plus n into 2 pi is equal to xt, where n is any natural number, which is 1, 2, 3, 4, 5, 6, 7, 8, whatever, right? But look carefully, 2 pi is the minimum value here for which the signal, minimum value of time for which after which the signal actually repeats itself. So in this way, 2 pi is a period of the signal. This 2 into 2 pi is also a period of the signal. This 3 into 2 pi, that's also a period of the signal. But this one, the smallest value of the period, is known as the fundamental period of a signal, of the signal. So you already know then this simple sine t, this signal is periodic with a fundamental period of 2 pi, right? So if this is clear, we can proceed further with this. And simply say that a signal is considered periodic if it repeats itself after a predefined interval. So a signal is considered to be periodic if it repeats itself after a predefined interval. Or in fact, I would say a signal is considered periodic if it repeats itself systematically always after a certain predefined interval, right? So with that said, what is the fundamental period? And for a periodic signal, xt, okay, if there exists a real positive number say capital T, such that xt plus n into this capital T is xt again for any positive integer value of n, then the smallest possible value of t is called the fundamental period of the signal, right? Right. I don't think there is any issue up to this point, right? Right. So subsequently, this is my next question. What is the period of xt? Say I have sine 2t here, say this signal. Instead of sine t, what is the period of sine 2t? Let me know. So again, the same idea here. Understandably, we understand the very simple fact that a simple sine theta plus 2 pi will always be sine theta, right? So with that knowledge, we can very easily say sine 2t plus 2 pi, that's equal to sine again 2t, right? So try understanding what we just did. Question is, we added 2 pi with 2t, right? But look at the form in which actually we wrote the signal, right? Yes, Obhi Vishwas, you are actually right. The period of the signal is indeed pi, right? Now let's see what happens here. So what we just added, we added 2 pi with 2t, right? So look at this one again. Okay, so we had xt, right? So what if I write xt plus pi? What is the value of xt plus pi for this? So I have xt, which is equal to sine 2t, right? So what is xt plus pi? Xt plus pi would be sine 2t plus, let me just get rid of this. It would be sine 2t plus pi, right? And this is again sine 2t plus 2 pi, right? So that's sine 2t, that's xt itself, right? So the period of this, of a fundamental period of this signal is this one. So we are saying the fundamental period of this signal is pi seconds, right? So I think that's clear, right? So without deriving, can someone let me know what is the, so instead of saying period, I would say rather say what is the fundamental period of say this signal, say sine 3t. So can anybody answer me in the live chat? What is the fundamental period of sine 3t? I would wait for someone to answer. So what is the fundamental period of sine 3t? Again, right? Obi is correct once again. So the idea is pretty simple, right? So you just add 2 pi here. So this is what you need to see in order to calculate this. This is what you need to see. You just have to add 2 pi with the signal, right? Because sine theta is periodic with a period of 2 pi. So I can say I understand that sine 3t plus 2 pi is equal to sine 3t, right? So wait a second. So sine 3t, right? So with that information, I can very easily say what. So we added 2 pi with 3t. So question is, what did we add with t? So that can be easily found by taking 3 common out of that, and I have t is 2 pi by 3. So that's again sine 3t. So in terms of the time or the independent variable, this is the fundamental period. So for this signal, the fundamental period is 2 pi by 3. Pretty easy to understand, right? Okay, right? Okay, this is not pi by 3. Obi might be thinking something else, I don't know, but this is not pi by 3. This is 2 pi by 3, right? Because we are adding 2 pi with 3t and trying to figure out what did we actually add with t, because again this is xt, right? We can go back. So this is how we figured out that the period of the signal was 2 pi, because here we added pi with t for this signal, and since there were the 2 outside, we already got a 2 pi here, and we eventually found xt here, right? So that signal is periodic with a period of 2 pi, period of pi here. And similarly, if we add 2 pi by 3 with t, that 3 will automatically cancel out, and eventually we would have sine 3t. Yes, right. So let me ask you yet another question. I think you got the hang of it, all of you. So what is the fundamental period of what about this? What is the fundamental period of, say, instead of saying say sine 3t, so what about 10 sine 3t? What is the fundamental period of this signal? What is the fundamental period of this signal? Right, what is the fundamental period of this signal? So can anybody answer? Yeah, right. It's again the fundamental period of 10 sine 3t is exactly the same as the fundamental period of sine 3t. This is simply because of the fact that this number, this scaling factor here, does not matter at all. For this signal again, the fundamental period is basically 2 pi by 3 once again. Okay, so the fundamental period is independent of that, right? Again the same thing. So right, I'm trying to clear up all the confusions that you people might have. So now question is, what about this? So So again, here this does not matter. So question, what about this? So I have this signal. Say something else, I don't know. Wait a second. So right, so we have a signal, again a sinusoid with a certain phase. So yeah, so this signal does not have a zero phase. It has the initial phase of 5 pi by 6, and again a magnitude of 10. But my question is, what is the period again? What is the period of this signal? Period entirely depends on this. Right? So again, the period for this signal is again the same like the previous one, 2 pi by 3 seconds, right? The same thing, right? And just I believe all of you already understand what is this 3 actually. What is this 3? This 3 is basically the frequency of the signal, right, in radian per second, right? So 3 radian per second is the frequency, right? So the period is again only dependent on the frequency here, right? So with that said, now let me ask you a slightly more complicated question. The question is, what is the fundamental period of this signal? Now my question is on this, say sine 2t plus sine 3t. What is the fundamental period of this signal? So can anybody answer the question? Yeah, right. You can say angular frequency if you're thinking about mechanical terminology here. Okay, because of this radian per second, right? But we can just in general call it frequency, right? Right. Question is, what is the fundamental period of this? Yeah, Obi is correct here. The fundamental period for this signal is 2 pi. And how did I get that? How do we get that? Try to understand what is the fundamental period of this signal. We already know that the fundamental period for this signal is pi, right? And what is the fundamental? Let's call it t1. And what is the fundamental period for this signal? It's 2 pi by 3. So we are trying to find out the fundamental period of the composition of this signal, right? No, it's not going to be the sum of the fundamental periods. No. It's not going to be the sum of the fundamental period. So what is fundamental period? Fundamental period is the minimum amount of time after which the whole signal will repeat itself, right? So the fundamental period is the minimum amount of time after which the whole signal will repeat itself. So now we have to find out the minimum amount of time after which the whole signal repeats itself. Again, I repeated myself thrice. Okay, so now what is the minimum amount of time after which this has an integer number of repetition, and this also has an integer number of repetition. So we are trying to find out the minimum amount of time after which this signal repeats itself a finite integer number of time, and this also repeats itself an integer number of time. Okay, so this is not going to be 5 pi by 3 as you might be thinking. Okay, right, those who are saying 2 pi, they are actually correct, right? So so what is the value? The value is simply the period of the whole signal is simply the LCM of T1 and T2, right? So what is the LCM of T1 and T2? Is here LCM of, we are calculating the LCM of pi and 2 pi by 3, right? And the LCM is simply 2 pi, right? So the LCM of pi and 2 pi by 3 is 2 pi. Now you can understand now, in how many pi's do I have in 2 pi? That's 2, right? And how many 2 pi by 3's do I have in 2 pi? I have 3 of them. So I can say, I can happily say here, so after, bad handwriting. So I can happily say after every 2 pi second, okay, after every 2 pi second, sine 2t repeats twice and sine 3t repeats thrice, right? So this is the minimum amount of time after which we have complete integer number of repetitions of each of the components of the original signal. So we can say after every 2 pi second, sine 2t plus sine 3t repeats one, so repeats once. So we have complete 2 repetition of this portion and 3 repetitions of this portion. So we have a full repetition, right? So again, if we go back, this signal has a period of, this composition has a period of 2 pi, which is basically the LCM of the individual sinusoidal components. So individual components here, right? So in that way, if any signal is actually composed of multiple periodic signals, like this one, this signal is composed of multiple periodic signals. So this is one periodic portion and this is one periodic portion. Then the periodics, then if the composition is periodic, then the period of the composition would be the LCM of the individual periods of the components, right? With that said, I just said if the composition is periodic. So we shall shortly see that there is indeed a possibility where a signal is composed of many periodic signals, but the resulting signal out of those compositions is not periodic. That can happen, contrary to our general wisdom, right? Even though the signal is composed of periodic signals, the total composition might not be periodic. So there is a test to identify that. No, the LCM is not 2 pi plus 2 pi by 3. Let me show you how to find LCM of fractions, right? So those who might be confused, LCM is not the sum of two things. So we are calculating the LCM of pi and 2 pi by 3, and I just said the LCM of this. So the general rule is, if I am calculating the LCM of two fractions like this, a comma b and c comma d, the LCM is calculated as the GCD of b comma d and the LCM of a comma c. So LCM of numerator and GCF or GCD of the denominator, right? So we are calculating the LCM of those who might be confused about the LCM. So this is 2 pi by 2 and this is 2 pi by 3. So treat them as fractions. So the LCM of this would be LCM LCM of 2 pi and 2 pi and a GCD of 2 and 3. So what do you think the LCM is? So LCM of 2 pi and 2 pi is 2 pi. And what is the greatest common divisor between 2 and 3? That's 1, right? So that's 2 pi. 2 pi is the LCM, right? So again, let me know in the live chat if you find it difficult to follow somehow. So Shambomoy, Devashish, can you follow that the LCM is 2 pi, not 5 pi by 3? Let me know if you can follow actually. Yeah, not the total, right? It's the LCM, because LCM is the minimum amount of time after which each of the composite portions, each of the compositions will repeat themselves, right? So LCM is the minimum amount of time after which each of the compositions will repeat itself, right? Okay, thank you. So I think we can proceed from this. So I have yet another question for you people. Answer this. So calculate the fundamental period of this 50 sine 2t minus 35 cos 3t. So if this is my signal, what is the fundamental period of this? Okay, just one more thing about the attendance for this class, even though it's not really necessary for me to take the attendance. Those who have commented in the live chat, they will already get the attendance, and those who haven't yet commented anything on the live chat, just please write the word attendance so that I can actually know you attended the live chat and stream, and I can give you the attendance, right? So in case you did not make any comment in the live chat, just write attendance so that actually I can write down your attendance, right? Yeah, all of you instead wrote 2 pi, that's fine. Yeah, so the answer is 2 pi, of course, because again, for this signal, the period is again 2 pi. The period is independent of anything that happens here, independent of this, it's independent of this, right? So it's entirely independent of any of these. So the answer is 2 pi, right? Again, same thing. So period is only dependent on the compositions of the signal, right? So I think, okay. So I think it's easy for anybody to understand. So now I have a slightly more difficult question, I would say, right? So this is my question now. So what is the fundamental period of this signal sine t plus sine pi t. So what is the fundamental period of this signal? So I would expect you people to actually try to figure it out and answer the question. So for this portion of the signal, the period is of course 2 pi, and for this portion of the signal, the period, what is the period for this? Can anybody tell me? What is the period of this portion? Again, those who joined late, we are talking about periodicity of the signals. So basically, fundamental period of this sine at is basically 2 pi by a, right? So what is the period of this? What is the period of this portion? What is the period of this portion? What is t2? Can anybody answer? What is t2? What is the period of sine pi t? Can anybody answer here? What is the period of sine pi t? Yeah. So coronavirus says the the period of sine pi t is 2, and that's correct, right? So okay, anybody who is actually using any alias for their name, please write your roll number or actually your actual name so that I can actually give you the attendance if you care. Otherwise, don't. So actually, the period here is simply, understandably, 2 pi by pi, right? That's 2, right? So I have two components of this signal. Okay, one component is periodic with a period of 2 pi, and another component is periodic with a period of 2, right? So this portion of the signal repeats itself after every 2 pi second, and this portion of the signal repeats itself after every 2 seconds. So understandably, both of the components, okay, I said write down your roll number in case you are using an alias instead of your actual name. If you are using your actual name, if you have your actual name in your Google account, you don't have to write down your roll number in that case. Or if you are using any alias like that coronavirus person, if you want your attendance, then please write down your actual name. Anyway, so funny live chat. Anyway, so this portion of the signal repeats itself after every 2 pi seconds, and this portion of the signal repeats itself after every 2 seconds, right? Right? So what is the period of the whole signal? What is the period of the entire composition here? What is the period of the entire signal? Okay, Shamomai says the answer is 2 pi, right? Right? So in order to calculate the period of the whole signal, let me do it with another ink. In order to find out the period of the whole signal, we just calculate the LCM of T1 and T2. So we say we are calculating wait a second. So we are calculating the LCM of 2 pi and 2, and that's equal to 2, right? That's equal to 2 pi, right? 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 So, right. No, actually, this is really wrong. Okay, this is wrong. This is wrong. Question is why exactly? So can anybody in the live chat tell me why exactly I just said what we just did is actually wrong? Can anybody tell me in the live chat? No, it won't even be pi, right? So the word fundamental says simply means that which is the minimum amount of time after which the signal repeats itself, right? So if the signal repeats itself after 2 pi seconds, the signal will also repeat itself after every 4 pi seconds. 4 pi is not the fundamental period. 2 pi is the fundamental period because that's the minimum amount of time. That the term minimum here is important, right? LCM, lowest common multiple, right? But unfortunately, this is not correct, right? Why? Why exactly is so? Why? So the answer is simple. Try to understand that we are trying to calculate the LCM between two very different quantities. What do I mean by that? Okay, so what is the purpose of an LCM? Say I am calculating the LCM of say 20 and say 25, right? So what is the LCM of that? You can very easily understand that the LCM is 100, right? So so why in 100 20 goes 5 times, right? And 25 goes 4 times. So we have this idea, right? So what is the minimum number of times? So this number is divisible by both this and this. So we have integer number of occurrences of this number inside this, and again integer number of occurrences of this number inside this. That's what an LCM is, right? LCM is, right? So, but what we just tried to do, we tried to calculate the LCM of 2 pi and 2, and we said, and wrongly, incorrectly, we said 2 pi. So, if this 2 pi is correct, if this is the LCM of these two values, then 2 pi goes in 2 pi, how many times? 1 time, and 2 goes in and 2 pi 1 time, pi times, right? But problem is with this pi times here, pi is an irrational quantity, right? Right. Since pi is an irrational quantity here, for irrational quantities, for rational numbers, you can always find out a number with which you can multiply a rational number to get an integer, right? So if you have a rational number is always expressible as a ratio of two integers. Irrational numbers are not, right? So you can multiply pi with anything. You can multiply pi, yes, Obi, you are correct. If you multiply pi, you can multiply pi with anything and it will never become an integer. Okay, it will never become an integer. So this is not a valid LCM, right? Because you can multiply these things with anything, but again, if you instead of saying saying 2 pi, if you say 4 pi, that's also incorrect. If you say 6 pi, that's also incorrect. All of these are incorrect simply because you can keep on multiplying the period with any number as big as possible, but still pi will remain a fraction because it's an irrational quantity. It cannot be expressed as a ratio of two integers. So by virtue of that, this entire idea is incorrect. So what did we just discover here? We simply discovered that sine t plus sine pi t is aperiodic, right? So this signal is aperiodic, even though the components of the signal are periodic in nature, right? Right. So how do I test? I can simply test this way. So we check the ratio of the two periods. So what was t1, the period of this? It was 2 pi, and the period of this was was 2. So the ratio was aperiodic, right? The ratio of the periods were aperiodic. This is irrational, right? So idea is, if the ratio of two numbers are irrational, their LCM do not exist. So if the ratio of two numbers is irrational, their period wait a second, their LCM I'm talking about, LCM does not exist. So if the ratio of two numbers is irrational, then their LCM does not exist, and simply because of that, this signal is aperiodic in nature, right? So aperiodic means not periodic. Again, LCM is the minimum amount of so LCM is the minimum quantity, okay, that is divisible by both the contenders. So one of the contender is 2 pi here and another contender is 2 here. So we are potentially trying to figure out what is the minimum positive real number, okay, which can be divisible by both of them. But unfortunately, if the ratio is irrational, LCM in fact does not exist. And that is why the signal is aperiodic, so non-periodic in nature. Right. So I think I would end this discussion with a homework. Say, so let me know the answer of this question later on. Okay. Right. So we are moving on to the next topic. So I think this is fine, right? So we are moving on to the next topic here. So, right. So next point of discussion here. So we are now discussing energy and power of signals. So we have discussed enough about periodicity of signals, and now let's move into this energy and power of signals. And just before we can actually go into this, let me just tell you something. Signals that are non-periodic in nature, in fact aperiodic in nature, can often be considered to be periodic with a period equal to infinity. So aperiodic signals, we can theoretically, for the sake of doing mathematics, we often assume that aperiodic signals, signals that are not periodic, we consider them to have a period of infinite period, right? Something like that. So yes, the answer would be the LCM of all the periods, all the individual periods, if the LCM actually exists, right? The LCM actually exists, and so the answer would be the LCM of all these quantities, LCM of all the individual periods. Anyway, so now we are moving into talking about energy and power of signals, right? So with that said, let me draw a very simple electrical circuit, right? We are electrical engineers after all. Say this is Vt. Right, so we have a static component, a resistor, simple resistor, right? So, right, all of you already know that the current here is simply 1 by R into the instantaneous voltage. So at any given instance, that's the relationship, right? But my question is, what is the instantaneous power here? So instantaneous power is simply current into voltage, right? Voltage across the resistor is Vt, and the current through the resistor is It. So Vt into It. Yeah, that's very simple to understand. So we are just kind of simplifying things here because things are not as easy like this. But yeah, for the sake of simplicity, we are simplifying things. Right. So again, It is 1 by R. So I can say this is 1 by R V square. Okay, those who are getting confused with this, the period of this is pi. The period of this is 2 pi by 3, and the period of this is 2 pi by 4, which is pi by 2. Right? So the period of this is pi, period of this is 2 pi by 3, and period of this is pi by 2. Right? So I am trying to calculate the LCM of pi, 2 pi by 3, and pi by 3. Sorry, 2 pi by 3 and pi by 2. Okay. What is that LCM? Those who are, answering 6 pi, what is the LCM of pi, 2 pi by 3 and pi by 2? Yes, that's 2 pi. That's not 6 pi, that's 2 pi. You consider this pi to be pi by 1 for simplicity. So we are calculating the LCM of the numerator divided by the GCD of the denominator. So in the GCD, so we have pi by 1, right? So GCD of 1, 3 and 2 is 1, and the LCM of pi, 2 pi and pi is 2 pi. So 2 pi is the answer. So this signal is periodic with a period of 2 pi, right? Right. Anyway, let's get into the next one. So what we can see simply that power so this is the excitation, right? This is the input to the system. This is the excitation. So if this is the excitation to the system, the power, instantaneous power, is proportional to the square of the excitation, often, right? The square of the input, square of the amplitude of the input, to be very specific here, right? Right. So with that said, with this idea, in signal analysis, we define the power content of a signal. Okay, so again, just try to understand this. If this is how power is proportional to the square of the amplitude of a signal, we can say, so if xt is a signal, then we can say that the power of the signal is somewhat kind of proportional to the square of the signal, right? We're taking this Euclidean norm symbols here just to keep it in a generalized form, but for all intents and purposes you can assume this to be modulus. So let's just do that. Instead of saying the Euclidean norm thing, let's say right, so power is proportional to this. But what is energy then? What is energy? Energy is power that you spend over time. So total power that you can spend over time. So this signal, for this signal xt, this is proportional to the power in that signal, right? So if you multiply power with time, what do you get? You get instantaneous energy of the signal. And if you integrate that instantaneous energy of the signal over time, what do you get? You get the total energy. So this is often given as E subscript infinity. Okay, this is the total energy of a signal. This is how we define total energy of a signal. Right. If there is any confusion with this, let me know. Okay, one more thing. If you are answering something incorrectly, I do not really mind at all, because what is important is that you are trying. So you don't have to redact your message. Okay. You don't have to retract your message. You can keep it absolutely without any issue. So right, let's move on. Right, so this is how we define the energy of a signal. So let's draw a signal. Why not? Say this is xt. We are just solving an example, right? So right, so we are trying to, for example, we are trying to find out the energy content in this signal, right? So mathematically speaking, this signal can be written piecewise as this. This signal has a value of 5 as long as time is between these and the signal is 0 otherwise. So question is, find E infinity. So find the total energy of this signal. Right. Right. Question is, my question to you is, can anybody actually do the integration and find the total energy in this signal? Yeah, all of is correct here. So anybody else got it? Did anyone else get it? What is the total energy of the signal? Okay. Okay. Why do you think, Obi? Why do you think it's 125? So again, let's start, huh? Let's try. So we are calculating the E infinity or the total energy of this signal, right? Total energy of this signal. So what is the total energy of the signal? It's integral. It's this integral, right? Right? It is this integration, right? So for this integral, but look carefully. I can just simplify this upper limits and lower limits. No, Rishabh, that's not. It's not that large. Yeah, it's going to be 75. Let's see how. Okay, so again, this signal is 0 beyond t equal to 0 on the left and beyond t equal to 3 on the right. So right away we can change the limit of the integration from 0 to 3, because beyond that, beyond those time limits, the signal's value is 0, right? Yes, it's 75. So the value is 0, right? So with that said, this is the limit of the integration. Okay, and what is the value of the signal within that limit? We already know that this is 5, right? So I have 5 square, so 5 square. So that's the total energy of the signal. So if you do the integration, this is 25 and simply 25 into 3, right? That's 25, and we have t 0 as the lower limit, upper limit is 3, and that's going to be 75. You can say 75 joules, but instead of 75 joules, I would request you to say 75 units. Don't say 75 joules, because I did not tell you whether the unit of xt is volt or something like that, right? Xt could be something else. So don't say 75 joules or something, just say 75 units. That's it. Because I'm not, I haven't given you any unit, right? So you cannot just randomly put a unit here. That's one of the important things to understand here. Again, in signal analysis, this is just a representative term. It might or might not be 75 something. Okay, it's at least understandably, it's at least proportional to 75. That is what we actually want to understand here. Yeah, Shamama is right. So it's from integration from 0 to 3 and on 5 square dt, right? So I think it's understandably correct. So very simple, right? So anybody who did not get this, did not understand this, if there is anybody who did not understand this, please let me know. I would explain this once more. Right. So let's move on. So I have yet another question for you. So let's draw yet another signal. I'm having trouble drawing anything. But let's hope actually you can see. And same, this signal is simply e to the power minus t ut. So you might be already familiar with signals of this form, right? From your circuit theory classes, right? So this multiplication with ut simply means that the signal starts at t equal to 0. Okay, if I don't multiply this with ut, the signal would have started from minus infinity, right? So just multiplication with ut indicates that this signal starts at t equal to 0, because ut itself starts at t equal to 0. Before that it's actually 0. And we have it multiplied with e to the power minus t. So at t equal to 0, the value of the signal is 1. So my question is, for this signal, again, find the total energy. So again, can anybody find the total energy in this signal? Again, E infinity, that's the total energy, would be from minus infinity, this integration, right? Minus infinity to infinity, xt square dt, right? So can anybody do the integration and let me know what is the total energy in this signal? So in the live stream, can anybody calculate this? Obishay says it's infinity. No, it's not infinity. Arup says half. So let's proceed with this. We are doing this integration, right, from 0 minus infinity to infinity. But again, the first thing we should do is finding out what is the actual viable limit here. Again, the signal beyond t equal to 0 in the left. So before t equal to 0, the value of the signal is 0, right? So with that said, I can start the change the lower limit to 0, right? And the upper limit is infinity, because before t equal to 0 the signal was 0, so I don't need that. So I have e to the power minus t. I'm just skipping ut because ut served its purpose of changing the limits, and dt. So right, so that is what we are actually calculating here. So Obi, I think you might have put minus infinity here. That's why you got an infinity. So the lower limit must be 0 here, simply because we have the signal multiplied with ut. So before t equal to 0, the value of the signal was 0, right? If you have got that, I can proceed further with this integration. So this actually equals to, So if you do the simplification here, so you're saying minus half. No, let me just do the integration. You will see. So I have e to the power minus 2t dt, right? Right? Right. So what is this? This is integration. So if we just do the integration, we have e to the power minus 2t by minus 2 and 0 to infinity. And if we put infinity here, it becomes 0, and if we put 0 here, it becomes 1 by minus. So that's half unit. Yeah, if you're correct, so all of you are correct, I think. So the energy of the signal is half unit. That's pretty simple, right? Yeah. And as a matter of fact, the energy of this these in this sense, the total energy of a signal cannot be negative, because we are already putting a modulus and a square like that. So even if the value amplitude of the signal is negative, the modulus and the square will automatically make it positive. So energy cannot be negative in this sense. So there are other ways in which we describe energy of signals, energy of things, but in this context, this is how we define the total energy in a signal. Okay. So as an exercise, find the total energy. This would be an exercise for you. Find E infinity for this signal, e to the power minus t square, and say ut. So that will be your homework. And I believe all of you have got the resource materials. We have plenty of sample problems there. Try solving those problems and get back to me in case if you face any difficulty. Right. So now let's ask you yet another question. So let me just go back. Okay. Yeah. Write down. So this signal is ut, right? So my question is, find E infinity. Can somebody find the total energy contained in unit step? So this is the Heaviside unit step signal. Can anyone find out the total energy in this? Right. So again, the total energy in this signal is the infinity from so Manish says 0, Arup says infinite, Obi says infinite. Actually, infinite is the correct answer. Let's see how. So the energy is defined as this. We have written it so many times, right? So again, the signal has a value of 0. Yeah, Shamabai says integration from 0 to infinity ut. That's correct. So again, the signal has a value of 0 before t equal to 0. So I can again truncate the limit from 0 to infinity, right? From minus infinity to infinity, it has now become from 0 to infinity, because before t equal to 0, the value of ut was 0, right? And the value of ut within this limit is 1. So I have 1 square dt. So I technically have t and the upper limit to be infinity and lower limit to be 0. So the result is infinity. So this indicates infinite energy. Yeah. So this signal has infinite amount of energy, infinite energy technically. Right? With that said, let's move on and define power. Or rather, let me just define and give you the actual proper technical term. Time average power. So if you recall, the energy or the power, okay, was proportional. Instantaneous power was proportional to this, right? Square of the amplitude of the signal. Instantaneous power was proportional to this. But if we do this integration, then we get the total energy, right? Total energy. But instead of doing that, if I modify the limit and say over a period of 2t, we are integrating the signal. So we are, instead of calculating the total energy of the signal, we are now calculating the energy of the signal over a total time of 2t. Okay, so this is the total energy of the signal over a total time of 2t. And now divide the total energy of the signal over a time of 2t by 2t. So this is the total energy over a certain amount of time divided by that amount of time, right? This gives you that time averaged power of a signal. Right. So thing is, if xt is periodic with a period of 2t, then this is the time averaged power of the signal. And if xt is aperiodic, we do the same thing. We calculate something similar again. But recall that if a signal is aperiodic, so non-periodic in nature, then we can also treat the signal as a periodic signal with an infinite period. So if xt is aperiodic, we can just modify this with t tending to infinity. So this is valid if xt is aperiodic. So aperiodic is non-periodic. So that is how we define time averaged power of signals. Right. So let's again go back and recall that moments ago we found that ut has infinite amount of energy in it, right? Moments ago we found that ut has infinite amount of energy. So we calculated E infinity for this. So let's now go forward, and my question to you is this: find P infinity for the unit step signal. So can anybody find out the P infinity or time averaged power for the unit step signal? Obi says 0. No, it won't be 0. Okay, one more thing. The stream is going to go on for 30 more minutes approximately. So please hold on. You would get bored sitting, staying at home anyway. So, right. Let's see. So, what is P infinity for this? First of all, which formula do I need to use for UT? UT is an aperiodic signal, right? So, since UT is an aperiodic signal, we have to use this expression, right, for calculating the time averaged power. So, power for this signal would be limit t tending to infinity 1 by 2t. Can anybody find the correct answer before I actually calculate this? So from minus t to t, right? I have ut, the square of that, and dt. That's the time average power. Obi, you are correct in many the answer that you have given. So if you write this in the exam, I will give you full marks. Don't worry. But my answer would be slightly different from yours. You will see. So you answered 1, it's correct. But again, my answer would be different, but that is also correct. Let's see what I mean by that. So that's t tending to infinity 1 by 2t. Now again, this is ut, right? Since this is ut, before t equal to 0, this signal has a 0 value. So instead of this, no, 2 is not the correct answer. So instead of this, I would say 0 to t, and the value of ut is 1 within that limit, is dt, and the integration is limit with this 1 by 2t. So what is the integral of this? That's t and upper limit t, lower limit 0, so that becomes t, right? So with that said, we have 1 by so we can understand this is what is the answer? What do you think? That will be simply half unit, right? So this is what we can do about it, right? So this is the total energy of the time average power of unit step. This is the convention used in the book by Alan Oppenheim. So I actually recommend this book, and this Alan Oppenheim is one of the legendary professors at MIT. So you can actually watch his videos available on YouTube. There is another convention for aperiodic signal. Let me get rid of this. Okay, this is the convention used by Oppenheim. And there is in fact another convention. So there is another convention for finding total energy, time averaged power for aperiodic signals. So if the signal actually starts from t equal to 0, we often actually have this kind of expression. This is also absolutely correct. In some books, you shall find this definition in some books. So actually, if you calculate the time average power of unit step with this definition, you would find that the time average power of unit step, P infinity for unit step, is actually 1 if you use this expression. But nevertheless, the idea is important here. Now let's again go back for a moment and recall that we calculated E infinity for this signal, e to the power minus t ut, and for this signal, what was the value of E infinity? E infinity was half unit, right, for this signal. So let me ask you a similar question now. We had this, so now find P infinity for e to the power minus t ut. So for this signal you calculated E infinity. Now try to find out P infinity for this signal. So what is the total power of this signal, average power of this signal? So again, let's do the calculation. I'm again using the definition used by Oppenheim. So again, this is an aperiodic signal, right? This signal does not repeat itself. So we are calculating P infinity for this, and P infinity would be limit t tending to infinity 1 by 2t integration from minus t to t xt square dt. Right. So if I calculate this, that will be limit t tending to infinity 1 by 2t. Again, since this signal is multiplied with ut, the value of the signal is, again, if you put a wrong answer, does not matter. You don't have to retract your answer. Right? We all learn by making mistakes. So right, so with that said, let's this signal starts at t equal to 0, so I can actually modify the limit of the integration and make it from 0 to t the same way we did earlier, and we can get rid of ut because that served its purpose of reducing the lower limit to 0, and I have dt, ut square actually. So if we integrate this, we have, so if we do carry on the calculation, yes, Shamoma is correct. The answer would be 0. Let's see how. This is infinity, and this is 1 by 2t, and this integration here gives me 0 to t e to the power minus 2t dt, and with that said, it is limit t tending to, no, it's not 0.25. Let's see. 1 by 2t. Coronavirus is wrong this time. So it wait a second. So this is e to the power minus 2t by minus 2, 0 to t, right? And this is limit t tending to infinity 1 by 2t, and put the upper limit and lower limit. So we have e to the power minus 2t by minus 2 minus of minus 2 and e to the power 0, so that's 1. Right. So now of course, if you put if you put t tending to infinity, look what happens. So t is a very large quantity, right? So with this limit in place, this actually goes to 0, right? Because t is a very large quantity. So so t tending to infinity. So this is actually 0, right? So this entire quantity becomes 0. And now with that said, we can actually write down this, right? T tending to infinity 1 by 2t, and we have a half, because this is the quantity that actually remains, right? But again, what do I have? I have limit with this. What do I have? I have limit t tending to infinity 1 by 4t, which is simply 0, right? So we have 1 by a very large quantity, so 0. So the time averaged power for this signal is 0, right? Look at the limit. We have t, those who are saying half, 0.25, things like that. Look at the limit carefully. We have 1 by 2t, 1 by 4t, and t is a very large quantity. So this is actually 0. So if you have any confusion regarding this, ask me a question on the live chat. If you have any question regarding this, if you find it difficult to follow, ask me a question again. Got it, right? So right, so I'm proceeding further. So we have seen two different kinds of signals so far, okay, as far the energy and power is concerned. So we have seen the example of ut. So for this ut, E infinity was infinite, but P infinity was finite, and it had a value of half. And then we saw a signal like e to the power minus t ut, which had E infinity of half but P infinity of 0, right? So we have seen examples like this, right? So this signal had infinite energy but finite power. So explaining this is, this signal has, so this signal has infinite energy but finite power, right? And this signal has finite energy but 0 power, right? So get this, right? So they have a specific classification with this. Okay, signals that have infinite energy but finite power, like this one. Okay, infinite energy but finite power, we call them a power signal. And this is quite understandable, right? This ut is nothing but turning a DC power source on, right? So DC power source, we say power source, right? So the signal coming from a power source will have to be a power signal. Okay, just as an exercise, do this at home. Okay, find P infinity and find E infinity and P infinity for sin t ut, right? Because again sin t ut is like a AC power source. You would see that P infinity will be finite but E infinity will be infinite. This is a power signal again. So power signals essentially carry infinite amount of power but finite amount of energy. Sorry, power signals carry infinite amount of energy but finite amount of power, right? And signals that have finite energy, wait, hold on. Signals that have finite energy but zero power are known as energy signals. Right. So we have done the classification of signal. I had I had another agenda here. So I was supposed to let's go back at the beginning of the slides, all the pages. I wanted to discuss even and odd symmetry in signals, but we shall do that at a later class. But we couldn't do it today. Okay, because it's already like the stream is going on for already like 140 minutes. Right. Right. So I will be waiting here for 10 more minutes, 5 or 10 more minutes. If anybody has any question regarding anything we discussed, for those who came late especially, you can ask me a question, I would answer. Okay. And please let me know about the experience of the live stream. If this was good, let me know. If this was bad, let me know. And if you have any question, let me know, most importantly. I'll be here for 10 more minutes and then we'll end the stream for today. And I would let you know about the future classes. Because this is going to be the new norm, right? This is the COVID-19 edition of TIU's classes. Okay, thank you, Manish. Yeah, I will give you the slides give you the PDF for this, PDF of the handout, and also the video would be available in the channel, right? So later on, if you click on the link, you would get to see replay of this video. So I won't be deleting the videos. So don't worry about that. Thank you, all of you. Thank you, all of you. Anyway, okay, if you have any question, please ask. So I'll be here for 5 or 6 more minutes. If you have any question, please ask. Thank you, all of you. Anyway, if you have any question, please ask. Right. So I would request you to actually go through the sample problem set that I actually gave you, and let me and get in touch with me. And more classes to YouTube live streaming and gaming days. Yeah, sure. I will let you know about the next classes, right? Because getting it set up was a hassle, first of all, but we actually got it through. So with that said, I will let you know about the next classes, and please go through the sample problem set, the books, and you also have the. Let me switch. Let me switch. So right. So I gave you the lecture plan. So try going through that. We actually discussed this. So and the page numbers are here. So this is from Oppenheim's book. We have this. Go through that. So on the next class, we shall be talking about time domain signal operations. So you can come prepared to the class if you wish. And anyway, in any case, we shall be discussing everything in detail. So don't worry about that. You shall be finding all the materials I have sent you on the group. So with that said, I'm ending the discussion today. So thank you all for joining the class, and I shall let you know about the future classes. So thank you all. Thank you very much.